Hi, hello, I'm Kiran Kumar from Nature of Physics and Art. Welcome to my channel. Today topic is electric field intensity and electric potential due to a uniformly charged long metal cylinder. Okay, so this is the metal cylinder of radius is capital R and length is capital L. And assuming the Gaussian cylinder dotted lines, that is radius is R and small r and length is capital L. Length is same only. See here, first I am going to write electric surface charge density sigma, which is equal to charge divided by area. So that area of the cylinder is 2 pi r into L. So then we can write charge, which is equal to 2 pi r L into sigma, is taken as equation number 1. And next we have to use the electric flux and find the total electric flux of the cylinder. For this, here we have 3 surfaces, in which 2 plane surfaces and 1 curved surface of the cylinder. So here electric flux is 0 due to the 2 plane surfaces, because of this is positive charged cylinder. So electric field is radially outward direction like this. Here electric field direction is like this, E bar. Here also electric field is outward direction. Here also electric field is outward direction. Right side also we can take electric field is outward direction. On the surface, on the curved surface, electric field is radially outward direction in all directions. See now continuation, here we can find electric flux, that is due to the plane surfaces is 0 and curved surface only we are getting. That's why I'm going to write first electric flux due to the plane surfaces is 0. Electric flux due to plane surfaces is 0 because of theta is equal to 90 degrees and cos 90 is equal to 0. And next electric flux proof, no need, already we did in remaining videos. Again we feel difficult because of same method only. That's why electric flux due to curved surface. So for curved surface, that is theta is equal to 0. So there is a small element, this is the ds bar, and E bar ds bar along the same direction, then theta is equal to 0 degrees. So here cos 0, which is equal to 1, electric flux phi, which is equal to closed integral E ds cos 0. So we can write electric flux is equal to, that is integral closed integral E into ds, like this we got electric flux. Now total flux we can write. So total flux, so that total flux is phi, which is equal to phi 1 plus phi 2 plus phi 3. Total flux phi, which is equal to phi 1 phi 2. So here phi 1, here we can take phi 2. So that is flux is 0 because of E bar and ds bar mutually perpendicular. Cos 90 is 0, 0 into anything 0. So we will get 0 plus 0. And next phi 3 value is closed integral E into ds we got. So for this we can write this value is closed integral E into ds, which is equal to q by epsilon naught. This is Gauss law. So I will use equation 1 and equation, this is 2. So based on that we will get the electric field intensity first outside the surface, second on the surface, next inside the surface. Step by step we will discuss. Just a second, I will clean the board. And continuation here, small r is greater than to capital R. See, clearly we can observe capital R is the radius of the cylinder and small r is the radius of the Gaussian cylinder. So then small r greater than to capital R. Here the equation 1 in equation 2. So the resultant equation is here closed integral A into ds, which is equal to 2 pi r L divided by epsilon naught. So we can write like this here, E into integral ds. So E into integral ds, that is Gaussian cylinder, is S, that is 2 pi r into L, which is equal to 2 pi r L divided by epsilon naught. 2 pi get cancel. Okay, L is get cancel. So we got V outside, okay, which is equal to, okay, the value is here sigma is here, sigma we forgot to write, sorry, and sigma divided by epsilon naught, and here capital R divided by small r. This is taken as equation number 1. This is outside the electric field of a, okay, uniformly positive charged metal cylinder. Okay, then we can discuss on the, so just a second. Okay, next second one is, that is small r is equal to capital R. Okay, so think practically. Here we got equation in which small r is equal to capital R, that would be get cancel, then E on the surface, so which is equal to sigma divided by epsilon naught. Small r capital R is get cancel, so this is taken as equation number, okay, 2. Already equation 2 taken, so this is 3 and this is 4. Okay, and next third one, so this, see here small r is less than to capital R. Okay, so then here electric field inside the cylinder is 0 because of there is no charge. That's why electric field intensity is 0. This is first one outside the cylinder, second on the cylinder, and third inside the cylinder. Inside the cylinder, what happened here, there is no charge inside the cylinder, that's why there is no electric field, that's why E in is equal to 0. Just a second, I will explain potential and also graph of this electric field intensity. Okay, now we can draw the graph between the electric field intensity and R. R on the x-axis, electric field intensity on the y-axis. Think practically here, electric field intensity outside E out, okay, is inversely proportional to the R because of capital R constant, sigma constant and epsilon naught constant. So inversely relation is there, E out is inversely proportional to the R, that is hyperbola graph. And small r is equal to capital R, we will get sigma by epsilon naught. We got already sigma by epsilon naught E on here, but inside is there is no electric field, that's why not taking. Okay, so this is about the electric field intensity of the metal cylinder, and we will discuss electric potential based on the same formulas. Just a second, I will come back. Already we did electric field intensity outside, on and in of a metal cylinder, and continuation I'm going to find electric potential based on the EVD relation. So for that, the basic formula, okay, dV, which is equal to minus E into dr. Okay, so now integration on both sides. Okay, so integral dV is equal to V minus integral E value is sigma by epsilon naught for first condition, capital R less than to the small r, nothing but small r is greater than to the capital R outside the cylinder. So the Gaussian cylinder is outside, so then we can write capital R, okay, into dr divided by r. Okay, here we will get v which is equal to v out, which is equal to minus sigma r divided by epsilon naught is common. This is integral dr divided by r. Okay, so this value is v out minus sigma into r divided by epsilon naught log base a r. This is the answer for the electric potential outside the cylinder, metal cylinder. Okay, and next we can write on the surface. On the surface, small r is equal capital R. We got this same formula, v which is equal to minus integral e into dr. Okay, so e value is sigma divided by epsilon naught. So we will get here v which is equal to minus sigma divided by epsilon naught into r, but small r is equal to capital R, but small r is equal to capital R. Okay, this is the second equation. So this is the potential second equation. Okay, so potentials first equation, potential second equation. Okay, and then third one, see, try to understand for third one, e in, so that v which is equal to closed integral here e into dr, but this value is 0. Okay, so dv is equal to 0, so that v is equal to constant. So v which is equal to, we can write same on the surface, inside also same potential. So for that, the potential equation is minus sigma divided by epsilon naught into r. This is the third equation for the potential. This is inside. Okay, so just a second, I will continue with another topic, that is non-conducting sphere, non-conducting cylinder.